So for right now, we will be doing the power system parameters lab. So firstly, so go ahead and you create your new case. Create the system shown in figure 1. Select the appropriate one line and case names. The relevant system data are shown in the appendix. Alright, so from the diagram in figure 1, we will start to construct the circuit. But before I do, let me just start right now. First, I'm gonna get the bus bars. .8 is good. Oh, name this one Hunts Baby 6. Alright. Second bus bar Huntsby. For Huntsby, the voltage of the bus bar would be 13.8 kV also. So yeah, that's correct. Alright. For the Huntsby A bus bar, we'll be doing that right now. The voltage of that one will be 69k kilovolts. Yeah, just double check. Yup. All right. So first we'll go ahead and start to connect the transformers. Yeah. We would now insert the values. So line X would be 0.14818, line R 0.00463, MVA limit would be 80 MVA. Okay. We would now be putting the parameters. It would be the same. A18 0.00463 MVA of AD. Yeah, the bus bar. Let's say stick right here. 3 lines. Oh, just a double check. Sixty-nine, 13.8. Alright. What I was doing, I was basically just double checking the nominal voltage of the bus bars. Alright. We want to park. Washington Boulevard. Alright, let me just put the generator from now. The bone up, yeah. So we will be configuring the generator for Huntsville B6. So that would be correct. AGC turned on, yes. Max would be 65.1. The minimum would be 0. MVAR max would be 42, and we would then like fill out the fault parameters. Just a moment. Let me set the set point. Powers 17 MVAR. Right. So where you see like R1 and X1 would represent the positive sequence, R2X2 negative sequence, RO XO 0 sequence. Neutral grounded, yes. Yes. Alright, so everything should be good. When I reach at lab 2, we will be playing with the part factor, really, but not for lab 1. Alright. Oh, let me enable Slack. Um, no. Slack is enabled using the bus bar. Yeah. These kind of look a little funny. So look. For Hunts Bay, this will be minimum 0, maximum 32, mvar output 21, mvar min 0. Yeah. Then choose the set point 25, 9. Should be it. Fault parameters will be the same process again. So for the positive sequence, neutral grounded. Yeah. So for this one, we would not be using the slack bus, just saying. Let's double check. 316. Okay. We will then add the second generator with the same specifications. Yep. Basically what this was saying, it was saying like there's already like a generator on that bus bar, so it was just like saying, hey, there's already one, but just click yes. Alright, so we'll be using the same specifications again. Set point 25, our output 9, minimum 0, MW max 32, in bar 0, and max 21. Yep. So 0.012, 0.316, 0.036, 0.301, 0.017, 0.316, neutrally grounded. Yep. What we can do, just just to differentiate, we can just like put a color, not a big deal really, but you could just do what the doctor do really. Yeah. Alright. So yeah, well, these have already so you can go ahead and connect the loads, or you can connect the transmission lines and the transformers. So what I'm gonna do first, I'm gonna connect the loads, Yeah. Should be like easy enough, I guess. Connect the loads. Alright. We'll then like look in the document for the load data. So edit mode, draw, network, load. We can add it like right at the exact end right there. So for this, the MW value for the Huntsville A would be 28.83. The MVAR would be 8.43, right? Basically, there's not like a MVA field. That's because, like, well, by putting the active power and the reactive, basically gives the like MVA in the background. Okay. Yeah. Right. Oh, just a minor fix, really. Is it left? Yeah, left. Yeah. Oh, also I can look up 0 plus J 8. Alright, so to confirm this, that it actually like gives 30 MVA, you can just like use a calculator and you would put the 28.83 as the active power and the 8.438 as the reactive, or you could say the imaginary, and you can convert to polar just to confirm. Yeah. So second load, Duane Park. Load at Duane Park would be 4.95 MW. 3.78. So using a calculator, you can again confirm the apparent power. Yep, up. Yeah. That's fine. Um, School for the Washington Boulevard. Washington would do 34.22, 2.15 up. Yeah. Um, you may notice that right here is missing the fields. You can just like add that at a later date. I'll show you though, like later on in the video. So yeah, 3 miles is a little bit up, so let me just bring that right there. Load. This will be pointing down, down, right? Um, 23.67, 12.2. Yeah, it should be fine. Should be fine. Alright, let me. Yeah, that's cool. Alright, so I guess what we have left to do is to just connect the transformers and the transmission lines, really. Alright, let me connect the transformer. So the transformer specifically says, alright, we're gonna run the transformer from Hunts Bay B6 to Hunts Bay A. So you have to make sure to do it in the exact order, really. So um, 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 oh yeah, really, yeah. Make sure you have these values though. Yeah, these are in the data sheet you were given. Um, the transformer 2 runs from Hunts Bay to Hunts Bay A also. Alright. So we'll use the same data again. Series resistance of 0.00463, series reactance of 0.14810. Yeah. Alright. So I guess we can start to run the transmission lines, really. So I guess we can run the Hunts Bay A to the 3 miles right now. So you draw for your line data. So alright. must be 83 mile. Alright, nominal voltage is confirmed 69, and the 69 comes from the bus bars. I would have set like initially 520 MVA limit 0.01323, reactance of 0.03004, and like in your data sheet you see line C. Line C would mean the shunt charge, so that's 0.0004. Then like you notice in your sheet will also say use the reactance values given for the zero sequence values. Just a moment. Alright, where was I? Oh yeah, so I was saying to use the reactance values given for the zero sequence values. So we would head like all the way over to fault info, and you're gonna use right here. So it says to use the reactance, so you would not use the R values, just the X and the C. 0.03004, 0.0004. Yep, that's all, folks. So I guess we're gonna deal with the. Alright, so based on the data for the Washington to 3 miles, so based on the data sheet, it's saying that we should run the transmission line from 3 miles to Washington Boulevard. So make sure to do that. Alright. Bum, bum, bum. So from the data sheet again, nominal correct, MVA 410, series resistance 0.01575, series reactance 0.03529, shunt 0.00307. Yeah. For now, we would do the same for the X and the C values. What's this? 3.03529. 0.0007. So what we can do, we can know the transmission line for the connecting Hornsby A and Duane Park. So according to the sheet, yeah, it's from Hornsby to Duane. Hornsby. Oh shit. Language. Hornsby to Duane Park. So it's just the same process all over again. So datasheet 410 series resistance 0.03361, reactance 0.04957, 0.0014. Now we have the last remaining one from Duane Park to Washington Boulevard. Where's that? Alright, so according to the sheet, you should run it from Washington to Duane. So Washington to Duane 410 series 0.02247, 0.4474, 0.0008, fault. These belong to right here. Oh, ensure to save your work, you know. Where can I save this? Power system. Mm. Practice lab 1. Yeah. Mm, yeah. That's okay. So according to the lab, what should we do now? Having created the system, solve the load flow and determine the real and reactive port dissipated absorbed by each transmission line. I'm gonna do a test right now. Um, Usually, if when you start to run these and the values change, there's maybe something wrong somewhere. So let's see. Oh yeah, that's cool. All right, that's cool. That's cool. That's cool. Um, I mean, if I must be honest, like the first time I did this, I had many problems, but you know, you are what you repeatedly do. Therefore, excellence ought to be a habit, not an act. Don't you forget that. All right, so go back to edit mode. we can start to like, alright. So since we need the solve the load flow and determine the real and reactive power dissipated observed by each transmission line. So what you can do right now, you can go back to draw field, um, transmission line field. By touching that, you can see the real and reactive. So this is the real field, reactive. So for this lab, basically what we would be doing would like to you know basically this is basically like an introduction to the software. So you will figure out like how to get the load flow, um, the reactive, the active, and all those stuff, and notice what change in the susceptance values. If you remember what I did for the fault info for each of the transmission lines, I changed the susceptance values. But like when I reach at lab 2, that's the that's the power flow, you will get to realize that the injection of reactive power will like significantly impact the voltage of the bus bar. And like when you like inject the active power, there will be like a significant increase on the load slash the bus angle. But yeah, that's later on tonight. So yeah, in here. Nope, nope. If that comes up, always say no. Okay. um, yeah. Here we go. VR flow. So nope. So what you have here is a fully functional circuit. Um, I'm wondering if I should just do the entire lab right now, like do everything. All right. So let me just do the first part really. So select any line and use the given design data along with bus bar voltage from load flow to draw the equivalent circuit and calculate it. Oh, um, for the susceptance, for the susceptance, yeah, I'm gonna show you. So I had a request from one of the subscribers to go over the whole fault thing. when they say to vary the susceptance values between 0 and twice the given, but so basically when they say to play with the susceptance, they mean like, let's say you touch a line. Where the susceptance values between 0 and twice the given value. So it would be just a moment. Susceptance. Um, Susceptance is the imaginary part of the admittance. So just point of info though. Hold a message from Schoolology. Oh, just a moment. Alright, so for the susceptance thing, they want you to go in like increments, right? Oh my bad. Just a moment. Alright, so back to what we were doing. So we're saying to vary the susceptance values between 0 and twice the given values, right? So when they say susceptance, they refer to the imaginary part, you know? So basically for the first like instance, for the imaginary value, you would like zero it, right? You would zero the imaginary part, and then like you will then record the impact, if like any, on the active and the reactive power flows in each line, After dealing with that, what I want you to do next for part C of part 1 is to double the double the negative sequence reactances for each transmission line and determine the impact on the bus voltages and the line currents. So for part C, they're referring that um you play with right here basically. So you would double these. So part 2 says to change the network's base MVA to 150, 200, and 250 and determine the per unit and actual line currents. So I mean, these stuff are self-explanatory, really. You would just go back in the same settings as you did and make the changes, really. But this is the fully functioning circuit. For lab 1, I think I utilized all the tools and components I needed to use. I think what I did not do was to show you how to get the current field, because it was talking about the current field for the transmission line. Let me see. So it would basically be right here. Amp flow, really. For the bus bar field, bus field, you know, bus voltage. It's recommended that you use the PU though, just to make life a little bit easier. So, you know, stuff like those. Um, oh yeah, part 5, which will be the ending of the lab, spoke about the contingency study. So basically what the contingency study deals with, it deals with so you have to determine like what would you basically do to the network that would cause like a catastrophic failure, really. So I'm gonna do one right now. Hopefully I remember. um Contingency analysis. So run mode, contingency, click that. What did I do? I right click, insert special, auto insert, because we're engineers, we're not supposed to work harder. So we will be conducting the contingency study for like all the components of this network. So single transmission line or transformer. Insert. Bam. Still have more stuff though. Bus. Yeah, we need it for the bus. 6 for the bus. Yeah. Do we need for the load though? Like, yeah, I think, yes, I think I did the load when I was doing mine. Yep. I don't think there's any more though, cause we did the transformer, bus, load. That should be, yeah, that should be fine. So run. Just a moment. Uh, Finished with 4 violations. Alright, so the violations represent that basically, put in a layman terms, if you trouble a certain component, let's say like these components, you know, the transform of a Huntsby B6 or the transform of a Huntsby, trouble dead, you see me? Trouble, you see me? So hopefully when you understand what I do still, you know, this is basically like a quick thing. Later on I'ma do the power flow. Can have a major project thing to deal with right now, so you know, this was just a quick thing we show you. We really need to know like for lab one really, you know. The other things are some little things you would like play around with, you know. You know, like a new phone. Yeah. So let me save this cause this may show Dr. Isaac's tomorrow still, you know. Yeah. Alright. Stop streaming.